Hello, everybody. This is Dr. Andrew Chrysler teaching electromagnetics at Idaho State University. In this video, I would like to talk with you about a very common problem in magnetostatics, which is the application of Ampere's law to determine the magnetic field for an infinite current sheet. So in this problem, which is in basically every electromagnetics textbook, you'll be given an infinite sheet of current. And this sheet of current could look or be drawn in a number of ways. But in this case, we'll imagine that this sheet is here. It stretches in an infinite direction in this way. So this is on the XY plane. But the current itself is in the positive X direction. So from our perspective, as drawn, let's imagine that there's an infinite sheet of current. We've sliced it in half, or we've sliced it somewhere on YZ plane. And we're now looking at it and we have the current coming straight at us. So using the Ampere's law cookbook, which is here, we're going to follow these 7 steps, which can lead you to a solution for the magnetic field in this case. So let's walk through these steps. So first, let's identify the symmetry properties of the current. So identifying the symmetry properties of this current, we know that the this current is going to be on, there's a plane here, right? And based on the symmetry, if the current out of the page, we can expect that the magnetic field is going to be equal on the top and bottom of the sheet. So the symmetry that we should expect is that H will be symmetric above and below. Now, we should also determine the direction of the magnetic field. So that's in this second step, we should determine the direction of the magnetic field. Okay, so recall that we said that this infinite sheet of current, we're going to imagine this being a set of many wires all next to each other with currents that are traveling straight toward us. So for one single wire, let's think about what the magnetic field for a single wire looks like so that we can determine what the magnetic field for this infinite sheet looks like. So for a single wire, we know that if we have a current that's traveling in this direction, right, by the right-hand rule, we know that the magnetic field is going to be wrapped around the current like this. So if we have a lot of wires and we've oriented them so that the current is coming straight at us, we could also view this like one wire in this direction. And we have the magnetic field wrapping around in this way. So you can do this by using your own right hand to see that this is the direction of the magnetic field. Now let's look at this wire, this single wire, where the current is coming out of the page, and notice that above it, right, we're going to have the magnetic field pointed in this direction, and below it, we will have the magnetic field pointed in this direction. So this is for one single wire. Now, what if we were to put many wires all side by side so that we have the magnetic field coming out of the page? So now we're starting to look like the problem in the problem statement. And again, we're on step 2, which says we should determine the direction of the magnetic field. So determining the direction, let's look. If we have many wires like this, we could see that the magnetic field is going to be pointed this way for this top of the wire, and this way for the bottom of the wire. Now, if we go on to this wire, okay, that is going to be the same thing. So if we have a lot of wires that are all right next to each other, such that it approximates an infinite sheet, we can see that the magnetic field is going to be pointed in this minus y direction above the plane and in the positive y direction below the plane, right? Because recall, our coordinate system looks like this. So above, we will say that we have the magnetic field pointed in the minus y direction, and below, we have the magnetic field pointed in the positive y direction. And in this, we are considering hy to be constant, okay? And the reason that we're considering it to be constant is because this whole plane, right, that we could imagine that this stretches infinitely. So all of this current stretches infinitely. And so if we're in the center or somewhere in the middle where we are not close to the edge at all, we can see that the magnetic field is going to be constant. It's going to have a constant magnitude no matter where you are in this plane. And so we'll call this hy, this magnitude, a constant. Okay, so we've gone through step 1 and then step 2. Now we're on step 3, where we need to decide how many different spatial regions the current distribution requires us to determine. So we want to, again, we're trying to find the magnetic field. So considering the current distribution, we should think about how many different regions we're going to want to calculate the result for. Now, in this problem, we are assuming, right, that this sheet of current is infinitely long, but in this direction, we are assuming that it is very, very thin. Okay, so that means that we don't have to consider solving for the magnetic field inside here. We don't need to find the magnetic field inside a semiconductor or inside any other region. So we only need to consider above and below. So we just have the two regions, which is really just one region, right? So by symmetry. So we need to find this above and below. All right, now step 4, we need to find an Amperian loop. Okay, so we should use an Amperian loop, and we should determine what that Amperian loop is going to be. All right, and I will show you how to find the Amperian loop in the next video.